Okay, let's start. Today we'll do log and exponential functions. Okay, so recall that we defined a new function ln x as integral from 1 to x 1 over t dt for positive x. Okay? So we expect logarithm to turn multiplication into addition, and we hope that someone will prepare tables and help us to multiply these things. Okay? But to prepare the tables were difficult, and it later was discovered by pure accident that this function behaves exactly as you would expect a log function. Okay? So some properties of this. So fundamental theorem of calculus says that this is differentiable. Of calculus says that this function is differentiable, and in fact derivative of ln x is 1 over x. Okay, so this is in the domain x positive. Okay, so in particular it is continuous. It is continuous. Okay, we also showed that ln xy is equal to ln x plus ln y when xy are positive things. Ln, okay, let's say x over y is equal to ln x minus ln y. What else did we show? Ln x to the n is equal to n ln x. From the definition here, it is clear that ln 1 is equal to 0. And we showed ln 2. What did we show? Ln 2 is greater than 3 over 4. What did we show for this thing? Okay, so anyway, wherever we show this, ln 2 is greater than 1 over 2. Okay, so using this, we show that then limit x goes to infinity of ln x is infinite, and limit x goes to 0 from the right of ln x is minus infinite. Okay, so basically it follows from this and this. Okay, so we also noted that the function ln absolute value of x, which is defined as ln x if x is positive, and ln minus x if x is negative, has the same derivative as ln x, x positive. Okay. So this gives us a antiderivative and antiderivative formula integral of 1 over x dx is equal to ln absolute value of x plus a constant. Okay, so this extends the property of antiderivatives. And so what else did we do? What else did we do here? We also find this useful for integrals, for finding antiderivatives. It is useful to recall the chain rule with ln function. Okay, so if g of x is a differentiable function, ln of g of x is a function. Suppose g of x is always positive, never 0. Okay, then this makes sense. Okay, so g of x is differentiable and always positive on its domain. Then ln g of x is a differentiable function because you are composing two differentiable functions. You take its derivative. Chain rule says go either from outside to inside or inside out. Okay, so going this way, derivative of ln is 1 over g of x. Okay, then the derivative of inside is g prime x. Okay, so this is sometimes called the logarithmic differential. Okay, sometimes called the logarithmic differential. It's very useful because if g of x is a polynomial, okay, so you see that this one is a polynomial of degree less than 1, and every time, so if g of x is a polynomial, you write it as products of x minus roots. Okay, so let me give an example. In particular, if suppose g of x is a simple thing, x minus 1 times x minus 2. Okay, so then what is g prime x? G prime x is, okay, now apply the usual simple product rule. Derivative of this times this plus derivative of this times this. But derivative of this is 1. Okay, so this is x minus 1 plus x minus 2. Okay, I wrote it in the other way. Okay, so then if you look at g prime x over g of x, you see I divide this by this, so I have 1 over x minus 2 plus 1 over x minus 1. Okay, so it tells you it. So the numbers you have here, okay, so let me have the numbers here. This is 2. Okay, let me do it because now the number 1 represents the power of the 0, but it's not, it looks like a coincidence. Okay, so let me give those things. So suppose the multiple of this is 3. Okay, so let me give a number here which is not here and 7 here. Okay. Let's take the derivative of this. G prime of x equals 3x minus 1 square x minus 2 7 plus 7x minus 2 6 x minus 1 3. Okay, I took the derivative. Then you look at g prime x over g of x. Okay, I divide this by this. You see that I have 3 here. Everything cancels, but one of these x minus 1 does not cancel. Okay, so it stays there. Plus 7 remains here. All of this cancels with this, but an extra comes here. Okay, so now you see that these numbers are not just coincidence. These are nice. This is a nice way of finding the multiple, the multiplicity of the 0. Okay, so you have 3 here, you have 7 here. Okay, so you can check that if I had, instead of 3 here, if I had minus 3 here, take the derivative, you will have minus 3 here. Okay, so sometimes these things, well, next year, if you take complex analysis, these things are very crucial in understanding how functions behave. Okay. Well, in fact, these are the reasons, this thing and these things, these are the reasons why logarithm function is still used today. Okay, we just abandoned its practical use in turning multiplication into addition because we don't need it anymore. Okay, but the property that this function finds an antiderivative for 1 over x is very useful. Okay, so because we have antiderivative for all x to the n except n equals minus 1, and this one fills in that gap. Okay, so what else do we have? Okay, then we did some integration. So let me do some integration. Okay. Okay, so using ln x and its properties, its differentiation properties, we can integrate more functions. So this extends our repertoire of known functions. So next chapter, after we do these transcendental functions, next chapter is integration techniques. Integration technique basically involves taking a complicated function and reducing it to a form which you recognize. Okay? So this increases our repertoire of functions which we recognize. When you play with the integrand and bring it down to a function you recognize, the algorithm stops there and you take over. Well, that's also what happens in the softwares. They have a list, and if something is reduced to an element in the list, you get the answer. So one typical case was this thing, tangent x dx. Okay, so we want an antiderivative for this. This is very convenient for logarithm because you have sine x dx over cosine x. Let me write it the professional way. This is d minus cosine x. Okay, d minus cosine x over cosine x. So when you take this, so I have to multiply this minus 1 and this minus 1. So this gives me minus ln cosine x. Okay, so remember the formula we have here. If I recognize this, I put it inside here. So plus a constant. But minus this, it means that I have ln 1 over cosine x plus c. And this has a name, ln secant x plus c. Okay, so that actually what you do here is, of course, you substitute cosine, sine x. So actually in our mind, so this is our taut balloon. Here we said u equals cosine x, sine x. U equals, so if sometimes you think wrong, then nobody sees it, so that's okay. Okay, so du is minus cosine x dx. Okay, then we mentioned that we can use, so ln is also convenient in taking derivatives where we use this You say, I want to find the derivative of g of x. Okay. If I take the logarithm of this and take the derivative, we know that logarithm simplifies things. If you have, you use one way to use logarithmic function other than these technical deep stuff, which is very useful in complex analysis. But for calculus, this helps us in the following cases. When g is a product of several complicated things, when you take logarithm, it becomes addition. Okay, so now you just differentiate them one by one. But what you get is this thing. So you have to multiply what you get with g of x. Well, that's easy. Okay, so you end up finding g prime of x.
Didn't you should be cosine?
Hmm?
You should be cosine to get the last.
Okay, so this is our thought balloon. So I again change it. U equals cosine x. du equals minus sine x dx. Okay. Okay, now thank you for correcting this because this is recorded and everybody will stare at it later on. Okay, so let's give an example. Here I have an example from the book. So g of x, or let's say y, is equal to something x to the power 3, then square root x squared plus 1 divided by product of two things, let's say x plus 1 square, x plus 3, 4, just something like this. Okay. Well, if you have to do this by hand, then the easiest way is to do it by taking the logarithm, using logarithmic differentiation. Otherwise, you can always use your computer to find the derivative, simplify the result, and do whatever you like. But these are techniques from old times when you have to do these things by hand. So you look at ln y. Ln y is, I take the derivative of this. This is 3 ln x plus, this is 1 over 2 ln x squared plus 1 minus 2 ln x plus 1 and minus 4 ln x plus 3. Okay? Everybody agree with that? Now you take the derivative. Okay? Now take derivative of both sides with respect to x. Okay, so here you will have y prime over y, logarithmic derivative. Now this side is easy, 3 over x, okay, plus 1 over 2 times 1 over x squared plus 1 times 2x minus 2 over x plus 1 minus 4 times 1 over x plus 3. Okay, then y prime is equal to y times this whole thing. Okay, so that's your that's your answer. Now you simplify this if you need to. Okay, let's do a few more exercises because now we can solve differential equations. Let me check if I have differential equations here. I'll do this later. Okay, so these are for exponential function. So let me find some examples from here about logarithms and do a few more examples. So for example, let's do one differential. Let's do one exercise from each block to get used to this. Okay, so this says, for example, differentiate some function. So let's invent one function. So one of them is, so differentiate f of x equals x ln x plus 1. Okay, when we say plus 1, that's easy. So let's make this x squared. And now let's put plus 1. Okay, so f prime x is ln x, 1 times this is this, plus x times 1 over x plus 2x0. Okay, so this is generally something that you end up when you multiply x ln x and take the derivative. The derivative is 1 plus ln x. Okay, so what else? Okay, so sometimes there are things like this. f of x ln tangent square x. Okay, so these things are given to make it look complicated, but you notice that this is ln of square of something, so 2 comes down, ln tangent x. Okay, so that's generally one of the things to watch for in playing with the logarithms. If you have a complicated thing, watch for powers and take them out. Now, f prime x is easy. This is 2 times 1 over tangent x times secant square x. Okay, so if you want to simplify it, you can simplify it. The other one, the other type of things where this is useful is to solve differential equations. Okay, so solve for y if, so let me do a cooked up example so that we don't get complicated results. No, this is just for y and y frame. So let me see where. Okay, so y frame if y so where are these differential equations? Okay, so okay, so let's do some other type here. So the next part here, I'm skipping the part where they ask find f prime, f second prime, because they are all of this type. So let us go to find the equation of the tangent line to the curve at the given point. Okay, so this is something that we are interested in. So find the equation of the tangent line to the curve. Okay, let's look at which curve they give us. Y equals sine 2 times ln x. Okay, so to make it look complicated, at 1, 0. Okay, so if we are going to write the equation of a line, so we need a point where it passes from. So we have a point, then we need the slope. So slope is the derivative of this function at this point. Okay, so we need y prime at x equals 1. Okay, so y prime is equal to, again, chain rule here. Derivative of sine is cosine of what you see inside, plus times derivative of what you see inside, 2 over x. Okay, now since we need this, y prime at x equals 1 is equal to ln 1 is 0, cosine 0 is 1. Okay, so this is 2. 2 over 1 is 2. Okay, so here we recall that ln 1 is equal to 0, cosine 0 equals 1. Okay, so this just, we did this mentally. Okay, so we have y minus 0 equals 2 times x minus 1. So this is an equation of the tangent line at that point. So this is an equation of the tangent line. Okay, so the other exercise is just find y prime, giving these things. And use logarithmic differentiation to find something. So let's do one more. Well, okay, we did one example here. That's enough. Evaluate the integral. Oh, okay, so that's precisely the reason why we are doing transcendental functions, because they, among other things, they enrich our repertoire of antiderivatives. So let's play with some of them. But taking derivatives is half of the way you take derivative is by luck. So now I want your help for these things. Let's start with the easy one. I'll do the easy one. So this is 3 over t dt. So this is 3 ln t plus c. Okay, so I did the easy one. Now I want you to do one of these things. So integral of dx over something. Okay, so 5x plus 7, something like this. Okay, so what are your suggestions for this thing? Now that we are çalışıyor mu adam ya? Hı? Açma. Okay, now that we are in the topic of logarithms, we know that this will require a logarithm. So what logarithm do you want here? Okay, let's try that. U equals 5x plus 7. Then du equals 5 dx. I have dx here, so this is 1 over 5 du equals dx. So I can now substitute. Instead of dx, I'll write this. I take constant out, du over u. Okay, so this is 1 over 5 ln u plus c. Now I have to put this thing back. 1 over 5 ln 5x plus 7 plus c. With integration, you always check if this is going to work. Okay, so derivative of this is 1 over this times 5. This 5 cancels it, and we are done. Okay. So what else we have? Okay, so what do you say about this? So this looks horrible. So I'll ask you to solve it. This is from 4 to 9. In parentheses, square root of x plus 1 over square root of x square dx. Okay, what is your first move?
Take the square.
Take the square, yes. Why be intimidated with this? 4 to 9. Okay, so this is x plus 2 plus 1 over x dx. Okay, so now everything looks totally trivial. Okay, so this one is given to scare you, but your friend didn't get scared. Okay, so now we integrate this easily. This is 1 over 2 x squared plus 2x plus ln absolute value of x. Well, actually, everything is positive, so I don't need that. From 4 to 9. Okay, so we get some numbers here. Okay, so 1 over 2, 81 plus 18 plus ln 9 minus 1 over 2, 16 plus 8 plus ln 4. Okay, now if you have patience, you can simplify. In the exam, of course, you should simplify. In real life, of course, you simplify. You don't want to use this, okay? But in class, I'll leave it as an exercise to you to simplify it. Okay, so other places where we use logarithm to find antiderivatives is when you have 1 over x. And then logarithms, either on the top or on the below, on the denominator. Okay, so let's do those types of things. So for example, we can look at ln x over x dx. So this is one thing. And dx over x ln x. Okay, so let's do both of them. Let's see what happens. So here, what do you suggest?
Say u to ln x.
Okay, I'll say u to ln x. Then du is dx over x, which I already have here. And then this becomes u du, right? You are checking? Okay. So this is now 1 over 2 u squared plus c. And then, again, you put it back. 1 over 2 ln x squared plus c. Okay, so just pay slight attention here that ln x, everything squared is different than ln x squared. Okay, so sometimes you forget to put parentheses there, and then in the next line you simplify it by 2 ln x. Okay, so that's just one thing to watch for. Okay, so this worked here. As they say, if it is working, don't touch it. Let's try the same thing. If it doesn't work, then we'll come back and we try something else. Du dx over x. So fortunately, we again have the same thing here. So this is du, but this time u is in the denominator. Okay, so this tells us that this is now ln absolute u plus c. And again, I have to put this thing back. So this is ln absolute of ln x plus c. Okay, so we check that you take the derivative of this, 1 over ln goes down, then you have to take the derivative of ln x, that's again 1 over x. So this is correct. Okay, so how about something like this? Integral sine x dx over 57 plus cosine x. What do we do now?
57 plus cosine x equals.
Okay, so we try, let us try this. U equals 57 plus cosine x. Then du is minus sine x dx. Okay, so I have sine. Okay, let's do one more thing. Let us not be lazy. Let's use our brain only when it is necessary. Okay, so sine x dx is minus du, and this part is u, so minus comes out. I have du over u. Okay, so now this is minus ln u plus c, and this is minus ln, well, 57 plus cosine x is always positive, so I can write 57 plus cosine x plus c. And sometimes we don't like this minus here, sometimes we like it. So it is up to your taste to write it as 1 over 57 plus cosine x plus c. So you either prefer this one or you prefer the minus one side there. Okay, so okay, there is one part which says sketch the graph. So let us try to sketch the graph of ln x over x. But for that we need, I think we need L'Hopital's rule. Anyway, we'll try it. Okay, so sketch y equals ln x over x, x positive. Before we continue, we we'll look at the derivative. Okay, so this is calculus. So if you hesitate, you take the derivative. So y prime is derivative of this times this minus this times the derivative of this divided by x squared. So this is 1 minus ln x over x squared. Okay, so let's take the second derivative also, because now the derivative of this is minus 1 over x times 2x here plus, okay, so let's do the formula, minus 1 minus ln x 2x. Why did I write x here? This is 2 here. This is x to the 4. Okay. So this is minus x minus 2x plus 2x ln x over x to the 4. So this is not going to be any help to us. Minus 3x plus 2x ln x over x to the 4. So we can take x's out. So this is 2 ln x minus 3 over x cubed. Okay, so here we need, well, I'll talk about this in the next hour, so maybe we can leave it here. Okay, so we also need, since this is the interval, this is an open interval, we want to know the behavior of the graph when you approach the boundaries. So you have to take limit as x goes to 0 from the right, from this side, ln x over x, and limit x goes to infinity, ln x over x. Okay, so do you have any idea from high school what these limits are? What? Huh? Which one is 0? This one? Okay, this one is 0. Okay, so we'll do this later, this next week maybe, L'Hopital, using L'Hopital's rule. Okay, the derivative of this divided by the derivative of this will give the same limit. That's L'Hopital. So it will be the same. So it will be again infinite. Okay, so will that be infinite? You take the derivative of 1 over x. So okay, so this will be infinite. So so it must be minus infinite, right? If you take the derivative. Okay, so let's do this. We'll do this next week. So I took this exercise from the place where it says use computer. So because here I also need to talk about the exponential function. This is equal to 0 when x equals e. Okay, so I'm planning to do all that next hour. Let's check if we have other interesting things. In the last part, so this is what will be important. So how fast ln grows. Okay, so we'll do this later, but I'll show you something interesting, which will be also useful next semester, but also it has some consequences. Okay, so this is how fast does ln x grow. Okay, so we will use Riemann sums. So this is x, this is y. Okay, let me make this t, because remember ln x is equal to area from 1 to x 1 over t dt. Okay, so now this is the area under the curve. So let's do it like this. Let's do it a little bit like this. So suppose this is not to scale, of course. If this is 1, this is also 1, not to scale. Okay, so this is 1. Then we look at these numbers. Okay, so suppose this is n. Okay, so in between we have dot. Okay, so this area is ln n. Okay, so this is y equals 1 over t. So we see that this area is strictly less than the sum of these boxes. The first one is 1. The second one is, this is 1, this is 1 over 2, this is 1 over 3, etc. Okay. And if this is 1, so this is 1 over 2 plus 1 over 3 plus. And what is the area of this? This one is n minus 1, so this point is 1 over n minus 1 plus 1 over n minus 1. Okay, so let's use now black color to draw the lower Riemann sums. So these are now the lower Riemann sums. Okay. So ln x, the area is clearly larger than the sum of these boxes. But now I don't have this box. I start from here. So this sum starts from 1 over 2 plus 1 over 3 plus, and this time it goes up to 1 over n. So this is 1 over n. 1 over n. Okay. Now you can solve the following problem. Now consider the following question. Okay. So suppose a computer starts to add 1,000 terms per second of the sum 1 plus 1 over 2 plus 1 over 3 plus, okay, so 1 over 1,000 in 1 second, and plus, then it continues 1 over 2,000 in the second. Okay, so this one in 1 second, this one in 1 second, this is in 1 second, and it keeps adding these, starting from Big Bang. So Big Bang is capital, right? Because there are no two Big Bangs. Okay, so what will be the sum? Sum on New Year's Day 1/1/2000. Gelecek yıl kaç ya? 18. Okay, so how do you solve this? So what are your guesses? Suppose it starts at Big Bang, and at each second it adds 1,000 terms. Okay, so all civilizations always surprise us. At that time, there was a civilization at the beginning of that instant. They started this, they pushed the button, and it keeps adding these. Okay, so you find the age of the universe, change it to seconds. Okay, so that many terms. Okay, so if n is the age of the universe in seconds, then the question is summation n equals 1 to this big N, 1 over n equals what? approximately, of course, because you see, we can't exactly pinpoint the starting point within a second. So what are your guesses now? What do you mean 0? We are adding these things. We are not considering them one by one. You see, we are adding these things. Well, this part is smaller, and the last term is very, very small, but you are adding these things. No, why did we do this? So we are adding these things. Okay, so suppose I add 1. If you are adding so many billions and billions of terms, whether you add 1 or 2 doesn't matter. So the sum is approximately equal to this. Okay, so if I add, there is only 1 missing here. There is only 1 term missing here. So if you add these things, okay, so ln n is less than summation n equals 1 to n minus 1, and larger than summation n equals 2 to n, 1 over n. Okay, so on both sides, just one term is missing. So approximately, this is the answer. Okay, so what is this number? What do you guess that number is? Now you are all scared. You all believe that it is billions and billions, but you say, if I say billions, I'm sure it will be wrong. So let me say 0. 0 is also wrong. Okay, let's take a break while you sum up these things. And next hour, we'll continue with something else.